Hello, everyone. In this video, we will discuss calculus of vector-valued functions. Limits and continuity of vector-valued functions. Limits. Please refer to the following 3D space. Consider a space curve, where the arrowheads denote the direction of increasing parameter. Let r of t be the position vector for the parameter t, which is defined by the following vector-valued function, and the vector L be the position vector for a number c. As the parameter t approaches a number c, the vector r of t approaches the vector L. That is, the length and direction of the vector r of t emulate the length and direction of the limiting vector L. At the same time, the norm of the difference vector approaches 0. The limit of the vector-valued function, as the parameter approaches a number, is equal to the limiting vector, if and only if the limit of the norm of the difference between the vector-valued function and the limiting vector, as the parameter approaches the number, is equal to 0. This means that vector L is the limit of the vector-valued function as t approaches c if the length of the vector difference between the vector-valued function and vector L eventually becomes 0. T approaching c implies approaching c from both sides, even if only one side approaching c is illustrated. Note that the limit of a vector-valued function is a vector, just as the limit of a real-valued function is a number, as we have studied in Calculus 1. Now, instead of focusing on the position vectors, suppose we give our attention to the terminal points of the position vectors. Let P be the terminal point of r of t, while Q be the terminal point of vector L. As the parameter t approaches a number c, point P approaches point Q, which means the coordinates of point P approaches the coordinates of point Q. This means that the limit of a vector-valued function can be calculated by taking the limit of each component function, provided these limits exist. Continuity. Suppose Q is a point in the space curve where the value of the parameter is c. A vector-valued function is continuous at a number c if the limit of a vector-valued function, as t approaches c, is equal to the vector at t equals c. Which means the component functions are all continuous at t equals c. This equation tells us that a vector-valued function is continuous at a number if its limit can be computed by direct substitution of that number into the vector-valued function, which leads to a vector with real number components. L is a more general symbol for the limiting vector, while r of c refers to a vector that can be computed by direct substitution. The equation means that if the region near c is filled with vectors, then it is continuous at c if r of c fits into the region. Meanwhile, a vector-valued function is continuous on an open interval a, b, if, for every c in the open interval a, b, the limit of a vector-valued function, as t approaches c, is equal to the vector at t equals c. Note that this definition of continuity of a vector-valued function is similar to the definition of continuity of a real-valued function discussed in Calculus 1. Nevertheless, the continuity of a vector-valued function is an extension of continuity of a real-valued function to 3D space. Derivatives of vector-valued functions. Suppose R is a vector-valued function defined with differentiable component functions f, g, and h. Please refer to the following 3D space. Consider the space curve of a vector-valued function, where the arrowheads point to the direction of increasing parameter. Let P be a point where the parameter is t, while Q be a point where the parameter is t plus delta t. The position vectors of these points are r of t and r of t plus delta t, respectively. As delta t approaches 0, which means t plus delta t approaches t, r of t plus delta t approaches r of t, while the difference vector approaches a vector that touches the curve at only point P. The vector that touches the curve at that one point is called r' of t, and it is the derivative of r with respect to t. The derivative of r with respect to t is defined by the limit of the quotient of the difference vector and the change in parameter that caused the difference vector, as the change in parameter approaches 0, for all parameter t where the limit exists. Even though this illustration is for delta t greater than 0, the concepts are also valid for delta t less than 0, which means r of t plus delta t would be coming from the other side of r of t. Nevertheless, the direction at which r' of t points remains the same. From our previous discussion, the limit of a vector-valued function is computed from the limit of each component function. Hence, the derivative of a vector-valued function can also be written as the derivative of each component function. Geometric properties of the derivative. Consider a point on the curve where the value of the parameter is t0, and r of t0 is the position vector of the point. r' of t0 is the tangent vector to the curve defined by the vector-valued function r where t equals t0. In the figure, the vector r' of t0 is tangent to the curve at point P where t is equal to t0, and it points to the direction of increasing parameter. Meanwhile, r tangent of t is the tangent line to the curve defined by the vector-valued function r where t equals t0. In the figure, the line r tangent is tangent to the curve at point P where t is equal to t0. The equation of tangent line is given by the following vector equation. The first term is the position vector of the point where the line is required to pass through, while the vector in the second term is the direction vector of the line. Note that the discussion on the previous page is a generalization of the discussion here, which is focused on tangent vector and tangent line at a particular value of the parameter. T is the unit tangent vector which points to the direction of increasing parameter, just like r' of t. In the figure, the unit tangent vector points to the same direction as r' of t, the direction of increasing parameter. However, its magnitude is equal to 1. It is computed as the tangent vector, or the derivative of the vector-valued function, divided by its norm. Consider a vector-valued function that has a constant norm for all values of the parameter. This means that the space curve lies entirely on the surface of a sphere, which is a surface that consists of all points that have equal distances from the center. Please refer to the following 3D space. Consider a space curve that lies on the surface of a sphere. Differentiate both sides of the equation. Apply the product rule on the left side, and use the constant rule on the right side. The result is that the dot product of the vector-valued function and its derivative is equal to 0. This means that the vector-valued function and its derivative are orthogonal for all values of the parameter. Going back to the figure. For any point on the curve, the length of the position vector is the same as the radius of the sphere. Because the length of the position vector is constant, we can conclude that for any point on the curve, the position vector and its derivative are orthogonal. Integrals of vector-valued functions. Suppose the derivative of an unknown vector-valued function is known, and it is also a vector-valued function. How can we find the unknown vector-valued function? Please consider the following 3D space. Consider the space curve of the unknown vector-valued function, where the arrowheads point to the direction of increasing parameter. A specific value of the parameter leads to a point on the curve. This is the position vector of the point, and this is the tangent vector at the point. Meanwhile, these are the position vectors and their corresponding tangent vectors at different points on the curve. The unknown vector-valued function is solved by integrating both sides of the equation above, and then applying the fundamental theorem of calculus, which will be discussed later. Therefore, this is the unknown vector-valued function. It provides the position vector of any point on the curve. The first term refers to the position vector of the point the curve has to pass through, which is also known as the initial condition. While the second term refers to the vector-valued function for the path or the trajectory of the point beyond the initial condition. In the following discussion, we will focus on definitions and how to determine the integral of a vector-valued function. Let us start with indefinite integrals. Suppose we have an antiderivative of a vector-valued function, which means its derivative leads back to the vector-valued function. The indefinite integral of the continuous vector-valued function is the antiderivative of the vector-valued function plus an arbitrary constant vector. Recall from our previous discussion that the derivative of a vector-valued function is the derivative of the component functions. Hence, the indefinite integral of a vector-valued function is the indefinite integral of the component functions, and it is also a vector-valued function. Next, let us define definite integrals. Suppose a vector-valued function is continuous on the closed interval a, b. The definite integral of the vector-valued function from parameter equals a to parameter equals b is the limit of the Riemann sum of each component function, as the number of subintervals of the sum approaches positive infinity. Provided the limit exists. The definite integral is a constant vector, or a vector with constant components, while an indefinite integral is a vector-valued function, which is a vector with functions as components. The fundamental theorem of calculus states that differentiation and integration are inverse processes. Suppose a vector-valued function is continuous on a closed interval. Let the antiderivative of the vector-valued function be differentiable on the corresponding open interval. This means that the antiderivative is defined as the following integral. Then, the derivative of the antiderivative, or the derivative of the integral of a vector-valued function, leads back to the vector-valued function. Now let us go the opposite direction. The definite integral of the vector-valued function, or the integral of the derivative of the antiderivative, leads to the antiderivative. Specifically, the difference of the antiderivative at the endpoints of the closed interval. Thus, we can conclude that differentiation and integration cancel each other out, and the result of successive application of each process is the vector-valued function where both have been applied. These concepts are valid whenever a vector-valued function is an antiderivative of another vector-valued function, including continuity and differentiability requirements mentioned earlier. Moreover, these concepts work for any antiderivative vector-valued function pair, regardless of what symbol or variable were used. Going back to the illustration earlier, we had the derivative of an unknown vector-valued function equals another vector-valued function. Here, the antiderivative is the unknown vector-valued function. And we want to find its equation, given the point in space it must pass through and the vector-valued function of its tangents. Integrate both sides of the equation. On the left side, there is an integral of a derivative. So by the fundamental theorem of calculus, it is equal to the difference of the values of the unknown vector-valued function at the two limits of integration. On the right side, the variable u is just a placeholder for parameter t. Rearranging leads to the equation of the unknown vector-valued function. And it can be found by integrating the tangents, and making sure that the resulting smooth path passes through the point of the given initial condition. Please watch the next videos on how to solve problems about limits, continuity, derivatives, and integrals of vector-valued functions. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.